we have got this equation. EMF in the secondary coil is minus ns d phi by dt. So the alternating flux phi also induces an EMF called back EMF in the primary coil. So we also know there is a back EMF in the same coil itself, because the coil works like as mass and it opposes the change in current. So this EMF induced, which is called back EMF in the primary coil, it is equal to EP is equal to minus NP d phi by dt. So this is back EMF, this is the EMF in secondary coil, this is the EMF in primary coil. So but EP is equal to VP. So what is the meaning of EP is equal to VP? If this were not so, the primary current would be infinite, since the primary has zero resistance as it is assumed. So the meaning of this line is that there is some internal resistance, which is very less, and in that case what we have, this epsilon P is equal to Vp. Epsilon P is equal to Vp. Otherwise, if we assume there is zero resistance, the current in the circuit would be infinite. So we cannot assume zero current. We have to consider this equation where internal EMF of a cell, as we have learned, so this EMF must be equal to voltage, not to get current equal to infinity, because current cannot be infinity. We have already assumed zero resistance of the coil. So in case we put resistance equal to zero, so we get an infinite current if we don't put this equality. So that's why we are putting this equality. Now in the secondary coil, what we assume, secondary is open circuit. That means, what is open circuit? Open circuit means nothing is connected, on its end. So this is our secondary coil. So either it is open circuit or current taken is small. So we have attached some resistance which is such that the current taken from this secondary coil is very small. In that case, ES is equal to VS. So epsilon S is equal to again VS. So we are assuming in both the cases resistance is very small or this current is very small. So we have this equation, epsilon is equal to V plus IR. So either we are assuming R is very small or I is very small. In that case, so we can write epsilon is nearly equal to V, because this term is very small. So this internal resistance is very small. That's why we are writing this EP is equal to Vp, ES is equal to VS. So we have assumed this, where Vs is the voltage across the secondary coil. Now let us write these equations once again. So this is secondary, this is primary. So from this equation, let us put Vs. So Vs is equal to minus Ns d phi by dt. Ep is changed into Vp. Vp is equal to minus Np d phi by dt. So we have changed Es and Ep into Vs and Vp. Let us divide these two equations. So Vs upon Vp. So what we get, this will cancel out. Minus minus also cancel out. Ns upon Np. Ns upon Np. So what is the meaning of this line? This has a very important meaning. That means voltage on secondary coil, will change the primary voltage in ratio of number of turns in secondary and primary coil. So in this way, because this number of turns is in our hand, so we can change the primary voltage into any voltage by changing this number of turns in primary and secondary coils. So note that the above relation has been obtained using three assumptions. So what were three assumptions? The primary resistance and current are small. So we have assumed that in the primary resistance and current are very small. So that's why we assume this IR is very small or nearly equal to 0. The same flux link both primary and secondary coil, as very little flux escapes from the core. So what we have assumed, the flux is completely going into second coil. And third is the secondary current is also small. So secondary current is also small. In that case, we can use this IR also equal to 0. So if the transformer is assumed to be 100% efficient, that means it is not losing any energy. So what will happen in this case? So power is equal to IV. So since the transformer is 100% efficient, so current in primary into voltage into primary, so this is power input must be equal to power output. So transformer is not losing any energy. So current in secondary is equal to, so power output is current in secondary into voltage into secondary. So what we have done, input power is equal to output power, IPVP is equal to ISVS. So although some energy is lost, but for most of the transformer efficiency is around 95%. So 95% on 95%, this is a good approximation. This is a good approximation. Now what we have seen, this Vs upon Vp was Ns upon Np. Ns upon Np. Now let us put it here. So Ip upon Is is equal to Vs upon Vp is equal to Ns upon Np. Ns upon Np. So what we can see here, what we can see that if voltage is increasing, current must reduce. If current is increasing, voltage must reduce, or if voltage is reduced, current must increase, and both are in proportion of this number of turns in the coils. Suppose this secondary has 10 turns and this primary has 20 turns. So voltage on secondary coil is reduced. It is half of the primary. It is half of the primary. But current in the primary will be doubled. Current in the secondary coil will be doubled just to maintain the constant power. So what are our equation of the transformer? This is our equations for a transformer. So this is how a transformer affects the voltage and current. So Vs is equal to Ns upon Np, Vp, and Is is equal to Np upon Ns, Ip. So here we have, what we have done, we have written in capital letters, that means these are RMS value. Why we have written RMS value? Because I and V both oscillate with the same frequency. So when voltage is maximum, current is also maximum. So that's why we have taken RMS value. So same equation holds true for RMS values. So important thing from these equations. So voltage on secondary, suppose secondary coil has more turns. So secondary has 20, primary has 10 turns. So secondary voltage on secondary coil will be increased in comparison to primary coil. It is doubled. It is doubled. But current in the secondary is reduced to half, because this was 10 and this is 20. So voltage is doubled, current is halved, or if voltage is reduced, current will be doubled. So the relation is opposite for current and voltage. So that is, if the secondary coil has a greater number of turns than the primary coil, so we have assumed Ns is greater than Np, the voltage is stepped up. So voltage is increased. This type of arrangement is called step up transformer. In a step up transformer, what we do, we increase the voltage. However, in this arrangement, current is less in the secondary than in primary. So voltage is increased, current is reduced, and this arrangement is called step up transformer. So we always consider voltage, whether voltage is increasing or voltage is decreasing. If voltage is increasing, this is step up. If voltage is decreasing, we say step down. If the secondary coil has less turn than primary, we have a step down transformer. That means voltage is reduced. So if voltage is reduced, step down, that means our mobile chargers, if voltage is increased, then step up generally at the powerhouse. The equation obtained above applied to ideal transformers without any energy loss. But in actual transformers, some energy loss occurs due to following reasons. First of all, there would be some flux leakage. So definitely not all the flux can be transferred to secondary coil, and this is generally due to poor design. So what we can do, it can be reduced by windings the primary and secondary coil one over the other. So first design on which both the primary and secondary coil were on the same arm, that is much better. Resistance of the winding. So we have assumed that there is no resistance, but generally there is a resistance in the windings, and that is I square R. So definitely in high current and low voltages windings, these are minimized using a thick wire. So what is the meaning of this? Definitely windings have some resistance, these coils have some resistance, it is not zero. If we keep the current high, low voltage, so what will happen? The current loss will be increased. Here we cannot change the current, because otherwise we will not get the desired voltage, so we cannot change. So what we do, we increase the thickness of the wire, so it can handle more current very easily and resistance is reduced. So we reduce the resistance by using thick wires. Eddy currents, so we have already learned about eddy currents. So the effect of eddy current is reduced by a laminated core. Hysteresis loss, so the magnetization of the core is repeatedly reversed. So we have seen that once up, another time down, up and down, so this magnetization is constantly reversed, and we have already learned about this hysteresis diagram. In hysteresis, energy is lost, so the resulting expenditure of energy in the core appears as heat. So we lost heat, some energy, just to reverse the magnetization every time. We can say 50, the frequency is 50 hertz, that means 50 times in a second, and is kept to a minimum by using a magnetic material which has a low hysteresis loss. So what we can use to reduce the hysteresis, we use a material which has low hysteresis loss. That's why we use soft iron. So we use soft iron just to reduce this hysteresis loss. So here is the working. The large scale transmission and distribution of electrical energy over long distances is done with use of transformer, that we have learned. The voltage output of generator is first stepped up, so the current is reduced and consequently I square R loss is cut down. It is then transmitted over long distances to n sub area station near the consumers. So first we step up to reduce the I square losses. The voltage is stepped down at the places, voltage is stepped down. It is further stepped down at distributing substations and utility poles before a power supply of 240 volts or 220 volt, let me write 220 volt, reaches at our home. First it is stepped up to reduce the I square loss, then the voltage is reduced by step down transformer. So now we have completed this 7th chapter. Now we will start the chapter 8th.